Hello everyone, welcome to the manufacturing processes class. In this video we're gonna discuss the machining operations. This is the third group of manufacturing processes that will involve the removal of part of the material in the form of a chip, as we discussed before. So this is one of the essential manufacturing processes that would be used for making products or used a lot in industry. So it is important to understand the fundamental of the theory of the metal cutting. We're gonna go deeply through this theory, but we're just gonna understand the concept of the metal cutting and how we can remove chip from the material and the different keywords in addition to the different and the concepts of the machining operations and processes. So starting with the definition, what does it mean machining? So machining, you could say that this is like a group, as we discussed very quick before. It is a group or a family of material removal processes. So this is the key condition here, that we should have material removal. If we didn't remove part of the material in the form of a chip, it means that there is no machining. We said that in metal forming that we can do changes to the material, but the main condition that the material should be in the solid state, and many of the operation, the volume of the material won't gonna change. But in machining, we should have a change in the volume. The volume, it should be decreasing, it should be removed. There should be part of the material that should be removed in the form of chip to have a successful machining operation. So this is the key idea of the machining process. So it is like a group of or a family of material removal processes that involve removal, as we said, of the material from a starting work part. This is the starting work part or work piece. This is, we can just abbreviate the word like work. WP stands for work piece or work part. So this is the raw material, and as I said, we should have removal of part of the material in the form of a chip. So the remaining part of the material will be the desired geometry or the final product that we're already seeking. This is the basic idea of the machining operation. So like as shown here in the schematic, we're gonna use tools. So this is gonna be the cutting tool. This is the tool, and it is commonly known as cutting. Cutting, this word, we're gonna use it a lot since we're already talking about machining. Cutting, it means that this is the essential action that the tool should do to the workpiece. Like the tool should cut part of the workpiece in the form of a chip to be removed. So if there is no cutting, there is no machining. So machining kind of cutting part of the material or slicing a material. Like if you do have a piece of material and you're gonna slice this material twice into two pieces, you could consider this is like like machining operation kind of. Okay, while shearing, it would be classified as the metal forming process, but also it would be considered as a machining process as long as one of the two parts that you sliced, when you slice the material, if one of the two parts won't gonna be used, so this could be considered somehow like machining because we already have removal of the material. In machining, there should be cutting action. This is the essential action that, as I said, that involves shearing the work material or the work part, that it should be sheared. And it should be sheared, it means that this is the shearing plane. It should be sheared over this material. And this part, this is gonna be the chip that I'm talking about. This chip will be removed and it won't gonna use it, and the new surface, the new product, this is the new product, or this is like the new surface that is gonna be formed up or removal of this chip. So this is the essential thing in machining, that we should have cutting action or shearing the work part to form a chip, and as the chip is removed, a new surface will be obtained. Okay, so this is the basic idea or concept of the machining. The essential thing again, that we should form a chip by removing part of the material using a tool. And this tool, it is commonly known as cutting tool. So to do machining, there are some essential requirements. There are 4 essential requirements basically. First of all, we should have a tool. And this tool, it should be with a sharp edge. Like to cut something from a workpiece, first of all, the tool, it should be stronger, in many of the cases, it is preferred to be stronger than the workpiece, and it should be with a sharp edge. Like for example, the knife that you're already using at home. To cut anything, you should have a knife, and the knife, it should be with a sharp edge. So it is typically the same idea. Like you should have a tool with a sharp edge, like as shown here in these graphs. So for example, if I give you an example of, assume that this is a workpiece and you're gonna use a tool, but this tool is just like this box. So as you can see, this tool has no sharp edges. If you try to or move this tool with respect to the workpiece, this is the workpiece, you're just gonna end up with some friction, but there is nothing would be removed essential that would be removed from the workpiece, right? So you could consider that there is no cutting in this case. But how about if we do have, this is the workpiece, this is the workpiece, but we did some even we did like a little bit inclination of this tool somehow, and we just moving this tool in this direction. So now we do have like a sharp edge. This is a sharp edge that has been formed. This is sharp edge, right? So upon forming this sharp edge, this tool would cut, so we may have end up with some cutting into this workpiece. So if this one had been penetrated down a little bit, somehow we're gonna end up with some chip that will be start to be formed, right? So this is gonna be the chip. So in this case, we're gonna end up with some cutting. So it means that there are some essential things. Not any tool that would be used for machining. The tool should with some specific requirements. First of all, the tool should be with a sharp edge. Another thing, that the tool should include a rack angle, a specific rack angle, and you should understand that the rack angle, it would be positive, it would be 0, or it would be negative. And I'm gonna let you know what is the rack angle. Also, the tool should include a clearance angle, and in many of the cases, the clearance angle should be positive value, right? So what is the clearance angle? It means that the tool should have some geometry, some angles. It should include some specific angles. Like for example, the clearance angle. What is the clearance angle? The clearance angle should be the angle between the flank. The flank, this is the bottom surface of the tool, and the new surface that is going to be formed from the work part. So this angle here, this is the clearance angle. You could say, for this tool, this is the clearance angle. And this clearance angle is essential to perform the cutting. With no clearance angle, there is no cutting, right? So here we do have clearance. You could say that we do have clearance angle, which definitely is going to be this alpha. We're going to give it the symbol alpha. This is the clearance angle. But for this case, no clearance angle. So no clearance angle, there is no cutting in consequence, right? So if there is no clearance angle for the tool, it means that there is no cutting operation that can be done. The essential angle that needed to perform the cutting operation is the clearance angle. And there are lots of functions and purposes for this clearance angle. We shall discuss them later. But for the rack angle is this angle. It is the angle between the top surface, which is commonly known as the rack surface, to the normal to the new surface, to the workpiece surface. This is the normal to the workpiece surface, and this is gonna be the top surface, and the angle between them is gonna be the rack angle, which is alpha, for example. So this is like another symbol, we can give it like beta. Anyway, we do have two different angles, like beta, which is the clearance angle, and this angle is gonna be the rack angle. So you could consider that this angle, this is the rack angle. Okay. This rack angle is important to allow for the easy removal of the chip, because the rack surface, this is the surface that will be in contact with the chip. Like this is the surface over which the chip will be sliding and removed from the work part. But the clearance surface or the flank surface, it won't gonna be in contact. There is no contact between the chip and the flank surface, but the chip is gonna go over the rack surface itself, right? So this is the rack surface, and we do have the clearance surface in addition to the, or a clearance angle in addition to the sharp edge. These are three essentials for the tool to perform a cutting operation. In addition, we should have a machine. Machining operation, you should have a machine to perform this machining process, right? So that's why, since many of these operations, they would require very high force, because we are performing this operation to metals, right? And metals are a strong material. It is hard for us to cut into a metal material, but you can easily cut on wood. So we do have one of the hand cutting operation that we cut into a wood, right? We can do it by hand, but to do the same cutting into a metal part, in many of the cases you require a machine, because you require very high forces that exceeds our limits as human beings. So that's why most of these operations, they require special tools and special machines, and that's why we got the name as machining operation. This is the general theory. It is metal cutting process. Like we discussed, metal forming process. In metal forming process, the material is going to be forming, taking a new shape up on exposing the material into high force to change its shape. This is the theory of metal forming. But in the theory of metal cutting, we have to cut the material. We have to remove part of the material through a chip. Okay? But this metal cutting operation, most of them, all of them, they do require machine. So that's why one of the essential requirements of this operation, that we should have a machine tool. This machine, it is commonly known as the machine tool. The machine tool, here we are not talking about the tool, but we are talking about the machine that is going to be used for this cutting operation. So that's why we got the name as machining. So machining, it means that the use of machine to do cutting of metal parts. This is another definition of the machining operation. So we should have a machine tool, which is the machine itself, that is going to be used for the cutting operation. And this machine should include some tools, other tools. Like we should have a method of holding the tool, which is the cutter itself, or we can call this one as the cutter that is going to cut into the work part. Also, we should have method for holding the workpiece. Also, we should produce, the machine should have the capability to produce relative movement between the tool and the workpiece. It is typically like when I tell you to cut a piece of orange. So the orange itself is going to be the work part or the workpiece. And you shall use a knife, right? The knife is gonna be the tool with a sharp edge, with all the specification of the tool that we discussed before, like including rack angle, clearance angle, in addition to sharp edge, right? So the workpiece, again, it is the orange. You do have the tool, which is the knife. Then what? To do cutting, you should hold the orange with one hand. So this hand is gonna be the method of holding the workpiece. And you should hold the knife from the other hand, using the other hand, your other hand. So this is going to be the method of holding the tool. You're already holding the tool. You should hold the tool. You should hold the orange with the other hand. Then what, you have to produce some relative movement with high force between them, so you could able to cut into this piece of orange. So this is the basic idea of the machining operation, and these are the essential requirements to do any machining operation generally, right? As I said, for the rack angle, it would be positive or zero or negative, but in many cases, this is gonna be positive. This is for the clearance angle. Like this case, the rack angle here, it is positive. If it goes from the normal, going to the right direction, so this is gonna be like the positive rack angle. It would be zero in case that the rack face is already considered over the normal of the surface. And it would be negative, like this case, we do have a negative rack angle. We would give a name to the clearance angle relief, because clearance or relief, they do the same concept. So this is like the relief angle or the clearance angle. And this point, it is not just point, because we're already representing this thing in 2 dimensions, but in the 3 dimension, it's going to be an edge. This edge is going to be the cutting edge that we're already talking about for the machining operation. So these are some essential concepts of the machining operation that we should understand. So how many operations? We do have lots of things. Generally speaking, any cutting of a part of the material, whatever the material is, this cutting operation is a machining, can be classified as a machining. How you cut from the material, this is a machining operation, okay? So machining, that's why some people would give it a name as material removal processes. Because material removal processes, many of them, they already done using machining, using machines. So that's why we would have the engineering name is machining. But the academic name kind of, it is material removal processes or metal cutting processes, especially if we are doing these things for cutting. So, or cutting processes in general. So the material removal processes would be classified into three main groups: into conventional machining, abrasive processes, and non-traditional machining, or traditional machining and non-traditional machining. Some people would include or combine these two into one group as the traditional machining. This is like traditional machining, and non-traditional machining, which is the other group. In the traditional machining, we should have a tool, and the tool, it should be in direct contact with the workpiece. But in non-traditional machining, in many of these operations, there is no direct contact between the tool and the workpiece. You got my point? So this is the big difference between the essential difference between these two operations. Like in traditional machining, we should have a direct physical contact between the tool and the workpiece. Like in this case, the tool, it should be cutting, so it should be in direct contact with the workpiece. There are lots of problems of this traditional machining. One of the essential things that this tool will be heated up. There would be some huge amount of temperature that would be, or heat that would be generated because of the friction between the tool and the workpiece. This friction, it is very high to increase the temperature of both the workpiece and the tool. And as we discussed before in metal cutting, the temperature, it do affect the mechanical properties of the material. So it would make the material more weak. So that's why we would have wear, this tool will be weird, and in addition that this tool would be broken down at excessive increase in the temperature. And we're gonna discuss these things. But anyway, in the traditional machining, we should have a direct contact between the tool and the workpiece. But in non-traditional machining, we came up with new methods that would involve cutting into the workpiece without direct contact of the tool to the workpiece. This part we won't gonna cover it through this course, because this should be covered in like there are even more than this list. We do have mechanical energy processor, electromechanical methods, we do have thermal, we do have chemical machining, chemical methods. So, but this operation usually covered in the non-traditional machining course and in another course. The abrasive processor, the most common type definitely is going to be the grinding operation, and in addition to some other abrasive processes, like for example, sharpening tools, like sharpening the knife. This is abrasive process. The sharpener that you're already using for the knife sharpening, we're already using like a grinding wheel. So this is the grinding operation. But through this part, we're gonna focus over these conventional machining operation, which like the turning operation, the drilling operation, the milling, and the shaping operation. So these four, we're gonna focus over 4 different types of machining operation that we're gonna discuss them. The objective is just to understand the operating principle of each one of these machining operation, the tool that would be used in addition to the machine. So 3 is in addition to the different operation that would be done. So like for example, in the turning operation, you should understand what does it mean turning operation and how it works, its operating principle. So this is the first thing. Also, you should know the name of the tool and the shape of the tool. What is the tool, the cutting tool that would be used for doing turning operation? What is the name of the machine and the shape of the machine? You should acknowledge the machine of this operation. Also, what are the different turning operations? We're gonna do the same for all of these different operations. This is what we are going to focus on through this part, right? So, but before doing so, let us discuss some of the machining conditions. And their relation to the metal removal rate. So the machining condition, this like the initial setup, like you have to do as engineer or operator for a machine. You're gonna use a machine, you have to arrangement, there is like a control panel of the machine, you have to adjust, and there are like lots of handle there to do control on or to give a specific value for the cutting speed, a specific value for the feed, a specific value for the depth of cut for a certain operation. Like for example, in order to cut, you're gonna have a tool and you're gonna have a workpiece. You're gonna fix them over the machine. We said that the machine should have a method of holding and fixing the workpiece. You should have another method of fixing and holding the tool. Then the machine is going to produce some relative movement between the tool and the workpiece. So this relative movement, it mean that the tool is going to move with a certain speed with respect to the workpiece. So this speed of movement, it is related to two velocities or two speeds. One is related to the feed rate, the other one is related to the cutting speed. We're gonna discuss these two keywords or these two conditions. Like these are the first thing that you have to set up. You have to adjust the cutting speed, you have to adjust the feed value, you have to adjust the depth of cut before you start any machining operation. You have to know these values. So for example, if you are an engineer in a workshop and you give an order to the operator to do cutting for a certain workpiece, the first thing that he's gonna ask you about it, what are the machining conditions? So the machining conditions are three essential things, which are the cutting speed, the feed, and the depth of cut. The cutting speed, this is the primary motion. This is essential to the cutting motion, or you could say that this is related to the cutting motion. This is the speed of the cutting motion, and this cutting motion will be different from one operation to the other operation when we discuss the concept of these of the different machining operation. The feed motion, this is a secondary motion, or it is commonly known as the feed motion. Right, so this feed motion, so we do have two motions that we should generate using any machine during any machining operation. One is a feed motion, one is a cutting motion. To understand these two operations, I'm gonna give you a very simple example of the driller. Like if you're already using a driller and you would like to drill into a hole into the wall, right? So in the drilling operation, using the driller, and this is gonna be the tool, the twisted drill. You're using like a sharp tool, like with some sharp edges, and you're gonna have the wool itself. And the objective is just to open a hole within this wool. So what you're gonna do, you're just gonna connect this one to the electricity, right? And you're just gonna switch it on. So what's gonna happen, you're gonna end up with some rotation to the tool. The tool will be rotating. This rotational motion, this is the cutting motion. This is one of the things. So this is the cutting motion. And this motion is essential. This is the primary motion. If this twisted drill won't gonna rotate, you won't gonna able to do any machining. So machining, it means that you're gonna open the hole. To open hole into the wall, this is machining operation, because definitely some of this wool will be removed in the form of a chip, because you're gonna remove part of this wool into the form of a chip, right? So this is machining operation. Cutting or opening hole into the wool using a driller, this is machining operation, very simple. The rotation of the twister drill is the cutting motion. Why the cutting motion? Because with no rotation for the tool, for the twisted drill, there is no hole would be open. You should have a connection to the electricity, and you should give rotation to the twisted drill. So this rotation, it is one action, one motion, which is essential thing. So that's why this is the cutting motion, right? And this cutting motion should be done at a certain rotational speed. So that's why we should have a specific cutting speed of the twisted drill. Then what? You have to feed, you have to push, like easy push. You have to easily push the twisted drill against the wall. You have to keep pushing. You have to keep penetrating and pushing the twisted drill against the wall. This pushing action and the movement of the twist drill inside the wool, so we do have another movement. This other movement, this is the feed motion that I'm talking about. This is the feed motion. So these two motions are essential to perform any machining operation. If there is no feed, if there is no cutting, there is no machining. But one of them is auxiliary, one of them is essential, one of them is, or primary, one of them is secondary. The primary thing, the first thing that you have to do, you have to turn on the twisted drill and you give it a rotation. So this is the cutting motion. Then you have to feed inside the workpiece. You have to feed inside the wool to open the hole. So these are the essential motions, and both they should be done at a specific speed. So for example, for the feed motion, while you give rotation to the twisted drill and you try to feed inside the wool, you have to feed slowly, very slow, to open the wool, right? The hole itself. So this is this feeding action inside the wool, it should be done at a certain speed. So that's why we would have a specific feed value or feed rate value, which is the speed of feeding inside the workpiece. In addition to these two cutting conditions, we do have an essential other thing, which is the depth of cut. This depth of cut is going to be, it defines the geometry, the final geometry that we have to do for the work path. It's going to be very clear when we discuss more as we move. I'm going to explain to you what does it mean, the depth of cut, but simply the depth of cut is related to the penetration of the tool into the original workpiece surface. How depth that you're going to cut, how much of metal that should be removed from the workpiece, this essentially depends on the depth of cut. So the multiplication of these three parameters or three machining condition gives metal removal rate. Metal removal rate, simply this is how much of volume of the material that it shall be removed in the form of chip per unit time. This is per unit time. So we could say that the metal removal rate, this is the volume of the metal that shall be removed by the cutting operation or the machining operation per unit time. So that's why it's unit, it should be volume per second, or like millimeter cube or meter cube per minute or per second, it depends. So the multiplication of V, which is the cutting speed, time the feed, time the depth of cut, this is gonna give us in general the metal removal rate. Also, this is one of the essential parameters that you should know for any cutting operation. So as I said, these are the four cutting operations that we're gonna focus on. As I said, we're gonna discuss some things related to the turning operation, like the operating principle, what is the tool, what is the machine, what are the different turning operations, the same thing for the drilling, milling, and shaping or planing operation. All right. So the first machining operation that we're gonna consider is the turning operation. Turning operation, it is mainly used for making cylindrical parts like these. All of these parts already cylindrical, so this is the essential thing, but definitely there are some other things that would be done or the turning operation can perform in addition to just making cylindrical parts. But this is the essential thing for the turning operation that is mainly used for making cylindrical or producing cylindrical parts, with the objective of decreasing the diameter from a certain value. So this is like the original diameter D0 of the material, and we are in interest in decreasing this diameter into another D, where D should be less than the D0 definitely, by removing part of the material in the form of a chip. So this is gonna can be easily done using turning operation. So this is the essential thing. What we're gonna discuss first about this operation is its operating principle, how it works, how we can do turning operation. To explain the operating principle for any machining process, your objective is just to explain how we can perform these three cutting conditions that we discussed before: the cutting speed, the feed, in addition to the depth of cut. How we can achieve, what is the shape of the cutting motion? Is it rotational motion? Is it a sliding motion? Who's the part who shall be doing the cutting motion? Who's the part that shall doing the feed motion, and how we can perform, or the shape of the feed motion? This is to explain the operating principle. Like, for example, the workpiece, it should be rotating. And this rotational motion of the workpiece motion or rotation, this is the cutting motion. So this is one of the essential things. It is different than the driller that we just explained. In the driller, the tool is the one that rotates to give the cutting motion. But here, the workpiece is the one that rotates to give the cutting motion. It is different thing, right? So for any machining operation, you should understand who is rotating, who is moving to achieve the cutting motion. Is it the tool? Is it the workpiece? For the turning operation, the workpiece is the one that rotates to achieve the cutting motion. So the rotation of the workpiece, this is the cutting motion, while the tool moves linearly parallel to the workpiece axis. It moves parallel to the workpiece axis. This is the workpiece that rotates, so the rotation of the workpiece, this is the cutting motion, while the tool is just moving horizontal. This horizontal movement is gonna be the feed motion in the cutting operation. There we're already feeding to put more material in front of the tool to be removed. So this is essential that you should understand about the turning operation. This is how it works. This is the explanation of the operating principle, that the tool should be rotating to achieve the cutting motion. The workpiece should be rotating to achieve the cutting motion, while the tool should be moving parallel to, in many of the cases it moves parallel, but it is not essential to move parallel. We would give inclination to this tool to move in an inclined angle with respect to the axis to end up with another shape. But essentially the tool should be moving, and the movement of the tool horizontally, this is gonna give us the, like the feed motion. Tool motion, it is parallel to the workpiece axis, this is the feed motion, and there is a depth of cut. The depth of cut, this is like the penetration perpendicular to the axis. How much of penetration that you already, or how much of chip that you would like to remove, this is basically related to the depth of cut. So for the turning operation, the penetration of the tool, like this distance, this a little bit small distance, this is gonna be the depth of cut that we're already talking about. So this depth of cut is in direction that is normal to the workpiece axis. These are the essential things, and this is how the turning operation is basically working. To explain this principle to you, let us consider this video. So this is like a typical shape of the lathe machine. As we are going to explain this machine, you're gonna have a spindle. This is the spindle, and the thing here in the middle, this is gonna be the workpiece itself. As already shown here, this is the spindle, and we're already using shock to fix the workpiece. And once we turn on the machine, this is gonna be the headstock. This part on the left is gonna be the headstock of the machine, and this is the carriage. This carriage is just moving horizontally over these slides. These are slides within this machine, and there's some other handles to control some position and doing some things as we're gonna explain. And the tool, it should be fixed here. This is the tool post that already holding the tool. So this is the method of fixing the tool in this machine, and we're already fixing the workpiece in the shock on this in this machine. So as we said, the machine, it should do three main functions. It should have a method of holding the workpiece. This chuck is the method of holding the workpiece, and this chuck is fixed to a spindle, and this spindle is already connected to some gears inside, into a gearbox inside the headstock that already hidden inside this gearbox. So once we turn on this machine, this bending is going to rotate to give rotation to the workpiece, right? So this is the method of holding the workpiece. Also, we already fixing the tool, which is a very small tool. We're gonna discuss about this tool over this tool post. So this is the other method of holding the tool. And then what, we have to produce some relative movement between them. This relative movement, it should be through three main conditions, which are the cutting speed, a specific cutting speed, and the feed motion or the feed speed, in addition to the depth of cut. So basically how it works, if we give rotation to this spindle, this spindle is just rotating, very simple, rotates in this way, and this is gonna be the workpiece, as I said. So basically, and this is the chuck. So before we start, what we do, we give rotation to this handle, we rotate this handle to control the depth of cut. How much of depth of cut that we have to achieve? We have to adjust the depth of cut first before doing the physical action. We're just gonna turn on the tool, we adjust the depth of cut, then what? We're gonna start give rotation. As you can see, this handle is rotating. We just rotating this handle to allow for this carriage to slide over the slider to the left in this way. As we give rotation, the tool will start to, as you can see, this vertical. Do you see? Let me just shift back a little bit. Like this normal, this movement in this direction, this is how we adjust the or define the depth of cut. Then as we feed this horizontal motion parallel to the workpiece, this is gonna be the feed motion, right? So then as you can see, the tool has a sharp edge, and as the workpiece rotates, there should be some chip that is gonna be removed. These things that already like cut it from these things that already removed, these are the chip that I'm talking about in this way. So this is the operating principle of this turning operation and how it works. Make sense? So now going back here to the shape of this machine. So as we said, this is like a typical shape of the standard lathe machine. Like you do have on the left here, this all of this part is the headstock. This is the headstock part. And this headstock include all the gears, and there are lots of handles here, like this handle, this one, right? One of them is the one on the top, this control, this handle control the carrying speed. This is the one that for the carrying speed. And this one for the feed speed. And we do have some other handles to control whatever you are interested in making, hand feeding or automatic feed, motion, it depends. So there are lots of other hands, like one hand for the spindle and the chuck and lots of things. This thing on the back here, this is the tail stock. This is the tail stock. And this thing that already moving in this direction, this just move right and left over these slides. This is the carriage of this one. And we should have here on the top, as I said, we said that we should have the tool post and that already holding the tool itself. And there are some other handles to control the manual, the feed or automatic feed, in addition to the depth of cut and other things. As you can see, if we zoom in a little bit, we're gonna have here the, you know, like the lead screw. This is gonna be the lead screw. And this lead screw, the thing, when it rotates, because it is connected to some gears inside the headstock, when it rotates, it gives like horizontal movement of this carriage over this slide. So there should be some slides here. All right. So this is how it works, and this is gonna be the chuck that's gonna be used. We can remove the chuck, by the way, and put another thing, another method for holding the workpiece. We're gonna discuss these methods. And we do have here the center. This is commonly known as the center, one of the tools. In case that we do have very long workpiece, so if we fix the piece from one end, it should be like cantilever thing, and we'll keep the other end free, this would result in some vibration because it is not stable at the end. So that's why we would move this one to hold the workpiece from the other side. And this is the handle. If we give rotation to this handle, this tailstock is going to slide this direction or this direction, right? Even we can remove this tailstock at all and we fix other things. So we can use this machine for multiple purposes, right? So this machine, what is the name of this machine? This is the lathe machine that is used for making turning operation. So the name of the process itself is turning operation. And the name of the machine that it's used for making turning operation, it is commonly known as the lathe machine. Make sense? And this is the operating principle of this operation. So we discussed the operating principle. We discussed the tool that would be used for making machining operation. Now let us move to the different turning operation, how we can do this turning operation, or the different forms or different operation. Essentially, as we mentioned, the turning operation, it shall be used for making, produces cylindrical parts, right? So in this case, this is like a case of straight cutting. What is a straight cutting? Like you have the tool moving parallel to the workpiece surface. So this is the straight turning operation. This is a straight cutting. For this case, the workpiece should be moving parallel to the workpiece surface. But in some other cases, we can use different tools, we can use different things to perform the turning operation. Like for example, in this case, the workpiece is moving parallel to the workpiece axis, so we're gonna end up with cylindrical bar. This operation is known as straight cutting or straight turning operation. But we may have the tool moving parallel to the workpiece, but it will not perform cutting to the, here we already performing cutting over the periphery or the circumference, the external surface of the cylindrical part. We are not machining this face, but if the tool is already moving in this direction, normal to the workpiece surface, so and it means that we are going to machine this face, so that's why it is named as facing operation. We may have the tool moving with an angle with respect to the workpiece surface. So we're gonna end up with taper operation, like we already performing tapering. We already taper like inclined surface or taper surface to the workpiece. So depends, we're still using the same tool. This tool is typically the same like this tool, But here, this one is moving parallel to the workpiece axis. So we're already doing straight cutting. If we're already moving the tool perpendicular to the workpiece axis, this is gonna give us turning operation that is named facing. We're already working over the face, so that's why it is named facing operation. If we're moving the tool with an angle with respect to the axis, this is gonna give us the taper operation with a taper angle that depend on the tapering that already, or an inclination that we're giving to the tool. Okay. Some other cases we would do like contour turning. Contour turning, it means that you're gonna have this tool somehow is moving in this direction, then we're gonna give rotation to the tool, then we're gonna move. So you are doing like contouring, like you try to shape this edge over the tool itself, but using the over the workpiece, using the cutting tool, but giving rotation and different inclinations of the tool as we perform the turning operation. This is not common operation that would be used for metal. We can do these things for wood. Okay, but in some cases we would use the same concept for forming and shaping and cutting also into metals. Like as I said, we give different rotations for the tool to perform or to form and shape a specific contour into the workpiece, so that's why it is named as contour turning. Form turning, we are using a special tool. This is going to be the tool, and the tool, it has a profile shape, and this profile shape is going to be imparted and printed over the workpiece itself as we give rotation to the workpiece. So what's happened basically for this case, for the form turning operation, that the tool rotates, the workpiece rotates, but the tool penetrates inside the workpiece. But in the meanwhile, the tool has a profile, has a specific shape that is going to be imparted or printed over the workpiece. We do have chamfering. Also the tool, it is very similar to the form operation. It would be included as form turning operation because we do have the tool. The tool, it will have an inclined surface and it's gonna be just feeding, already feeding in this direction to form this chamfer edge, like chamfering the edge. We would use the turning operation for cutting off. It means that we just gonna slice this cylindrical part into two pieces using a special tool, which is the cutting off tool. This is gonna be the tool, and for this case, the tool penetrates inside the workpiece, moving in this direction. So as you can see the difference between one operation to the other one, in some cases we may have the tool moving parallel to the axis, we may have the tool but moving perpendicular to the axis like the cutting off and the facing operation, or with an angle with respect to the axis. And in addition, we may have the tool with a certain shape or the conventional tool. This is what distinguishes one operation from the other. The common thing between all of this operation is that the tool, the workpiece rotates to achieve the cutting motion, the tool moves to achieve the feed motion. This is the common thing between all of these operations. So that's why all of them are grouped as turning operation, and we can perform them using the same machine, which is the lathe machine. Threading, we can do threading by machining operation. Threading, it means that you're gonna have the tool will have a special profile that depend on the shape of the thread itself, and we just gonna move, the tool moves parallel to the workpiece, and we give rotation to the workpiece, and depending on the speed of the movement of the tool and the rotation of the workpiece, we're gonna end up with the pitch and the profile of the specification of the thread. Also, pouring, this is one of the operations that would be done using the turning operation. Like in this case, the tool works inside the workpiece. Assume that the workpiece, it is hollow, like it has a cavity, internal cavity, and would like to do turning or doing machining to the internal surface of the workpiece. So we're gonna use the pouring operation, and in this case, the tool is already working inside the workpiece. We would use it even for drilling. We can use the turning operation for drilling by removing the tailstock. To do so, we remove this center at the tailstock, and we fix here at twist drill. And we fix the workpiece on the other side, and we give rotation by hand to this tailstock to make the twisted drill penetrating inside the workpiece. So in this case, we're already forming a hole that is parallel, axial hole into the workpiece that is parallel to the axis of the workpiece itself. So this is also one of the operation. Knurling, this is one of the operation that would be done using the lathe machine. The objective is just to make this surface rough. As you can see in many tools, we already have these knurling things, that the objective actually is just to making rough surfaces so we can for hand purposes, for hand use. So this is a special tool, and that already fixed it to the tool stock, and the workpiece rotates, and this one is just moving parallel to the workpiece to form this knurling thing over the workpiece itself. So these are the different turning operation. The key idea is just to understand them, the difference between them in terms of the movement, the shape of the tool, and how the tool is already moving with respect to the workpiece. Make sense? Let us skip this part for now, and let us move to the different methods of holding the workpiece in a turning operation. We said that any machine, it should have a method of holding the workpiece. Like in the turning operation, how we can fix the workpiece. We do have different approaches. One of the things, we do have different methods. The common methods are using the chuck, but we do have two different chucks here. The first one is the three, or different types of chucks basically. The first one is the 3-jaw chuck, also is known as self-locking chuck. This chuck has 3 jaws. So this is one jaw, and we do have another one, and we do have a third one. So this is 3-jaw chuck. And we're already putting the workpiece here, then we're closing the chuck. So initially we open, we're moving this jaw. These jaws can be moved back, all right, can be opened. So we open the chuck. And how we can open it, this is the key chuck. This is the key chuck, or the chuck key. So we are using this key, and we put it here. This is the opening, this is the screw for the key, and we put this is a special one, and we just put this one here, and we give rotation. As we give rotation, you're gonna find these 3 jaws are sliding, moving, either toward the workpiece or outward, inward or outward, it depends. So we can give rotation to open this 4 jaws, and we just put the workpiece, then we close all of them together over the workpiece. But the good idea of this self-locking chuck, that only one key can be used for moving all the 3 jaws together. Like only one key is moving the 3. As you give rotation, the 3 jaws are moving. Not everyone is not moving separately with a special key, like the case of 4-jaw chuck, but for the 3-jaw chuck, we are using, this is the big difference between the 3-jaw chuck and the 4-jaw chuck. The essential thing for the 4-jaw chuck, we do have 3 jaws here, but there is 1 key for each jaw. Like there is 1 key for this one, there is another key for this one, there is another. It means that every one of the jaw can be moving separately. So it holds it used. That's why the 3-jaw chuck it mainly used for round and hexagonal work parts. So the work part should be symmetrical, it should be cylindrical, it should be circular, round. Why? To hold using the 3-jaw chuck, because the 3 are moving together to achieve very high symmetry in the material fixation with respect to the axis of the spindle, because there should be spindle. This is the spindle axis, that already the spindle of that rotates in the machine, and we should have the workpiece axis. Both axes should be coinciding together to end up with a perfect cutting, right? So grasps work quickly and accurate. It is very accurate. The 3 jaws move symmetrically when adjusting using the adjusted by the chuck key, as we explained. But in the 4-jaw chuck, it is used for hold round. It can be used for holding round workpiece, but we have to do so many precautions to achieve the like the symmetry in the axis of the rotation of the workpiece with respect to the axis of rotation of the spindle of the machine. Also, it can be used for a square, hexagonal, or any other irregular shapes. But in other words, the thing that you cannot fix using the 3-jaw chuck, the best option is to use the 4-jaw chuck that has 4 jaws, and each one is moving independently with independent chuck key. It has 4 jaws. Each one can be adjusted independently by chuck key. Jaws can be reversed or to hold workpiece from inside. Whatever the 3-jaw, we can hold the workpiece internally, not externally. There is no need even to explain this point to you. But let us move to the 3rd type of chucks here, which is the collet chuck. The collet chuck, and it is used for holding small work pieces, and it is very accurate with the small work pieces. It works with the same concept of your pencil. If you just open the pencil, you're gonna find sleeve. This sleeve is just slides, and this is the collet itself. It has 3 openings, 3 slots in this way. So initially we just put here, and as I said, this is like, assume that this is the lead of your pencil. This is the lead, and you just put the lead and you slide the sleeve over it just to hold, to squeeze or confine the workpiece inside the 3 slots of the collet itself. It is used for high precision working. Spring collets are available to hold ground. Also, it is used for holding, for fixing round, square, or hexagonal shaped workpieces. As I said, but the essential thing, the workpiece, it should be small workpiece. It is commonly used for this one, right? So the difference, we discussed the difference between these 3 cases, but the difference in terms of the shape of the workpiece. If you have a cylindrical work part, you have to use 3 cylindrical work part, and we would like to keep the axis of rotation of the workpiece coinciding to the axis of rotation of the spindle of the machine. The perfect option is the 3-jaw chuck. Unless the workpiece, it is a small workpiece, so in this case you have to use the collet chuck, right? But in case that you have a regular workpiece, or for some reason you have to achieve some eccentricity or shifting between the axis of rotation of the workpiece and the axis of rotation of the spindle of the machine, in this case the best option is going to be the 4-jaw chuck or 4-jaw independent chuck. Make sense? Also, one of the methods is the centers, is just using centers. Like in this case, like this is the center dug. This is just dug just to hold the workpiece, just to, like keep the workpiece in place against the pushing that comes from the tool. We're gonna discuss this point. So we are not using, this is the spindle already, it is not shown inside the machine. And this is gonna be one center. This is the center, one of the methods, and this is another center. And the thing in the middle that starts from here up to this step here, this is the workpiece in the middle here. This is the workpiece. So we already just holding the workpiece using 2 points. along the axis of the workpiece itself. One center from here, one center from here. Then we are using the cutting tool. The cutting tool, it just cuts in this direction. So we should have the tool already cutting in this direction. Okay, so as the tool cuts in this direction, it's gonna start to push the workpiece. So, and you're already holding the workpiece between using 2 points, 1 point from this side, 1 point from the other side, from this center and this center. So this tool for some reason would be like removed or like just leaving the centers, right? Like because you're just holding the workpiece using 2 points. So that's why we are using this dog that works against the tool, and it moves with the tool, by the way. It means that the tool is already on the other side of this dog. It is not seen from the other side. So as the tool pushes from this side, the dog is something that, you know, like resist or, you know, like give support to the workpiece against the pushing of the tool to keep the workpiece in place between the two centers. This is also one of the methods, and the good thing of this method that we can do machining to the entire length of the workpiece. It is different than the shock method. In the shock method, there should be part of the workpiece that should be inside the shock itself. So if we would like to machine the overall length, the whole workpiece part, we have to machine this part first, then we have to stop the machine, and then we're gonna unload the workpiece and switch the workpiece and fix it from the other side inside the shock. So the machine part will be reversed, and the workpiece will be reversed, and the machine part will be fixed inside the shock, and the unmachined part will be machined after a while. It means that we have to do the process into 2 times or into 2 processes, right? In case that we're already using any one of these shocks, as I said, because part of the workpiece definitely will be inside the workpiece, inside the shock itself. But if we are interested in machining the whole length of the work part at once without loading and unloading the workpiece and reversing the workpiece, which would take time, and this time is money, in this case the best option is just to use the centers. So this is for the turning operation, and this is what we would like to cover about this operation. Again, it's just to know the different methods of holding the workpiece, to know the different turning operations, to know the operating principle, the name of the machine that would be used for the turning operation. As for the tool itself, the tool that is used for the turning operation, it is commonly known as the single point cutting tool, and we're gonna discuss this part after we finish the other machining operations. But before we move to the next machining operation, let us go over this part that we already skipped here. It's just to know the difference between forming or copying machining process and generating machining process. This part is not necessary to be just for the turning operation. I'm talking about any machining process itself in general. The classification of the machining process or the machining process would be used for forming or generating surfaces. Forming surfaces or generating surfaces. Generating process, in this process, the work bar geometry is dependent on the feed trajectory or the movement of the cutting tool with respect to the workpiece. Workpiece geometry does not depend on the shape or the shape of the tool itself. Like, for example, this operation is a generating operation. Why? The tool moves parallel to the workpiece and the workpiece rotates. So the relative movement, the workpiece here, the surface or the shape of this surface, this cylindrical surface, depend on what? Depend on how the tool is already moving with respect to the workpiece. If we give inclination to the tool, if we make the tool moves inclined with respect to the axis of rotation of the workpiece, we're gonna end up with another surface. So this surface is generated, it is not formed. Why? Generated by the adjusting the motion of the tool with respect to the workpiece. If we make the tool moving perpendicular to the axis of rotation of the workpiece, we're gonna end up with another surface. So this is all of these are different forms of generating operation. So generally speaking, a generating operation is the operation in which the surface that is going to be generated by machining depends on what? Depends on how we are moving the tool with respect to the workpiece. Depends on the movement, but it does not depend on the shape of the tool. Like for example, this operation, it is generating operation. This generating operation. This is generating operation. But this also is a generating operation. The contouring, here the shape of the surface depends on how you move, how you give adjusting to the angles of the angle of the tool with respect to the axis of the workpiece, how you give rotation. So it needs like more experience to do so, right? So to end up with this contour shape. So this contour shape, it is a generating operation. But this one is a forming operation. Why? Here we are moving the tool, yes, perpendicular to the workpiece, but the shape of the surface depended on the shape of the tool, on the profile of the tool. So that's why it is a forming operation. It is turning operation, yes, but it is classified as forming operation, and this is the second group. The copying of forming operation, that the workpiece and part geometry depends on the tool shape. It is not dependent on how you're moving the tool with respect to the workpiece, but it do depend on the tool shape. The cutting edge of the tool and the part surface of the workpiece part, they should have the reverse shapes. Like this shape will be imparted to the workpiece. As I said, this part is not included here. This method, it should be included as generating process. Why it should be included as a generating process? Because basically it does not depend on the shape of the tool, but it depends on how you're moving the tool with respect to the workpiece. But this one, it do depend on the shape of the tool. So that's why this is forming process. This one depend also on the shape of the tool. The tool should be have an edge, and this edge should be typically the same size or the reversed shape of the chamfer, that we would like to impart or do to this workpiece. So it is a forming process. This one is not a forming process. We're just slicing, moving perpendicular to the workpiece. So this is generating process. Make sense? So these are examples of generating processes, but these are examples of forming process. This one is not included as forming process. This should be generating process. Generating process. But these two are forming processes. These are forming, or we can give it like copying, because you're already copying a special feature to the work part. So this is the copying processes. Make sense? Yeah. Also, we may have combination between forming and generating, like the case of the threads. The thread itself, this is a very common method of combination between forming and generating. Why? Because the tool is moving parallel to the workpiece axis, and as the workpiece rotates. So the speed by which the tool is moving and the workpiece rotates, these two speeds, they do control the pitch, the distance between one thread and the other one. So this distance here, the pitch distance, it do depend on the feed motion speed and the cutting motion speed. If you change the feed motion with respect to, if you are increasing the feed motion as we increasing the feed motion with respect to the cutting motion, so in this case we're gonna end up with wider pitch. So what does it mean? It means that the geometry, the shape of the final thread, it do depend on the relative movement, how you move the tool with respect to the workpiece. So that's why it is classified as generating. Another thing, that the shape of the thread itself, the shape of this thing, it would be triangular like the acme, or it would be like any other shape like square thread. The shape of the thread itself, it depends, the shape of the thread depend on what? Depends on the tool shape, So since the final profile or the final shape depend on the tool shape, it means that it is a forming operation. So that's why it is both of them. It is combination between forming and generating process, and the typical example to the combination case is the threading operation. Make sense? So this is for the turning operation, in addition to the difference between forming and generating operation. Now let us move to the next operation, which is the drilling operation that we explained before using the driller, right? So now let us go over the operating principle, which should be clear in this case after we explain the driller and opening a hole into the wall. It is typically the same. This is the workpiece, and the main objective of the drilling operation, it is mainly used for making holes, but in the turning operation, it is mainly used for making cylindrical parts. Here for this one, the tool rotates. The tool of the rotation, this is going to give us the cutting motion, and in the meanwhile it is fed inside the workpiece. So the tool movement comes through the tool, not the workpiece is just fixed. So we have fixed workpiece, and this workpiece is fixed over the table of the machine, and the twisted drill do two movements. One is rotation, the rotation of the twisted drill. This is the cutting motion, and it should be penetrating inside the workpiece to open the hole. This penetration motion perpendicular to the workpiece surface, this is the feed motion. So two rotates in the cutting motion, and the workpiece is fixed on the table of the machine. The feed motion is the tool that is perpendicular normal to the workpiece to open the hole, and the depth of cut definitely depends on the diameter of the twisted drill. Like the depth of cut, these are the three cutting conditions that we explained. There, the depth of cut, we adjusting it, but in the drilling operation, the depth of cut equals the half of the diameter of the twisted drill itself. This is the depth of cut, and it's going to be clear when we discuss the calculation of the machining time of this operation. So this is the shape of the twisted drill. This is the tool itself. Remember that we didn't discuss the tool that would be used for the lathe machine. We're gonna discuss this one, but after we finish this part, right? But here in the twisted drill, this is the geometry of the twisted drill. The twisted drill include two main parts, all right? Or three parts, essential parts, which are the shank. This shank, it would be straight like this case, or it would be tapered. What is the shank? The shank, it should be, this is the thing that is gonna be fixed in this spindle. In the twisted drill machine, we're gonna have a spindle, and the spindle of the twisted drill, it should be vertical in this way. And we just by hand, we're already fixing the twisted drill into the spindle of the machine. It's gonna be fixed. Just push this one against the spindle. This is gonna be the spindle of the drill press, and this is gonna be the twisted drill. This is the twist drill itself. By hand, you're just gonna push it against or inside the spindle is gonna be fixed there. Why? There is no need for more fixation to the tool, because it's gonna be pushed against the workpiece surface. So this pushing is gonna hold more, it's gonna fix more the tool, or keep the tool fixed inside the spindle. And as I said, the shank is the thing that is gonna be fitted and squeezed inside the spindle itself. This shank, it would be tapered or it would be straight, right? There is like a neck between the shank and the body. This is the body. This part is the body of the twisted drill. This is the neck, which is the thing in the middle. This is the neck that just separates the shank from the body of the twisted drill. And these are the cutting edges. So the twisted drill, it has two cutting edges. This is something that you should understand about the twisted drill. And the body, it is kind of twisted. This twisting is essential to allow for some fluids. So these fluids are essentially needed for the easy removal of the chip out of the hole. Because any tool, it should have a method of removing the chip, of getting rid of the chip out of the workpiece. Because as we give rotation to the twisted drill, more chip will be formed. We have to remove this one, right? Through these fluids, and these fluids were made twisted to allow for the easy removal of the chip, or the automatic removal of the chip as we give rotation to the twisted drill. But if these fluids are straight and we didn't do twisting to the twisted drill or to the drill itself, we have to remove the chip out of the hole by ourselves. Like it won't gonna be removed, the chip won't gonna be removed automatically. But because of the twisting thing, this chip will be removed out of the hole automatically as we give rotation to the tool. So the fluids allow for the chip removal from the hole, and we should, as I said, we should have like two cutting edges, but inside these two cutting edges, they won't gonna meet together at a point. No, they meet together at an edge. This edge, this little small edge here, is known as the chisel edge. This chisel edge, simply it is needed to initiate the cutting operation, and it should be small to allow for the tool penetration. So what does it mean this? For example, one of the theories, one of the concepts, or one of the things, like we would bring a tool like this one, and this tool, it is like these two cutting edges of the twisted drill, they're gonna meet together. This is gonna be the fluid in the middle here, this is gonna be the twisted drill, and the thing in the middle is gonna be the fluid. And assume that these two cutting edges, they're gonna meet together somehow over a point, and then you're gonna push the tool against the workpiece. So what's gonna happen? This point, it is a point, it means it is like a sharp edge, so the tool can be easily penetrate inside the workpiece, yes. But to start the cutting, basically this cutter is the thing that is going to cut. If this surface of the workpiece, it is very tough surface to allow for the tool to penetrate inside it, so it means that you do have like the tool will be over the surface at this point, and is gonna keep spinning with no cutting. Like you're already spinning something over a surface, right? But if we have this, you need like a chisel edge. If you cut this part and you achieve a small chisel edge, this edge will start, as it rotates, it will start to remove something, right? It will start to remove, and this is the thing that starts the cutting, and it is essential for this twisted drill. Without the chisel edge, there is no cutting could be done. So this is the essential function of the chisel edge. It is required to just initiate the cutting operation, but in the meanwhile, it should be small to allow for the further penetration of the tool inside the cutting edge. So this is for the geometry, and you should understand this geometry and understand these keywords here, that you should acknowledge that this is the shank, these are the fluids, the twisted drill has two cutting edges, there should be chisel edge, and you should understand the concept of the chisel edge and why you are using it for the cutting operation or the drilling operation. Make sense? Now let us move to the different operation that can be done using the drill press machine. There are lots of operations that can be classified as drilling operation. These are the essential thing, like opening holes. This is the essential purpose of a drilling operation, just to open hole, new hole. Whatever this hole is, through hole, like this case, this is a through hole, or it would be blank hole, like closed hole. It won't gonna be like through the wall part, right? So this is the essential operation. But in addition to opening hole, we can use the drilling operation for reaming. Reaming, it means that to like finish the surface. Like you should have a hole, and your objective is just to in case that the internal surface of this hole, it is very rough surface, and you would like to do finishing. Finishing, it means like you make this surface more smooth surface, so we can easily use it as customers. So basically, you should have a hole, and in this case, you're gonna use a reamer. This is the tool. It is as a reamer, but this tool, it is the twisted drill. So the twisted drill, it will be used only for opening hole. We are using the twisted drill for opening new hole, whatever, through hole or blank hole. But the reamer, it is used for finishing and hole that already opened before using a twisted drill. So in order to do, so basically what we are doing, we have to use the twisted drill first to open the hole, then we're gonna use the reamer to finish the surface, right, of the opened hole. Tapping, it is another method. We are using this tab, which is This is the tab which is used for making thread. So to make a threaded hole, we have to open the hole first using the twisted drill. Then we're gonna use the reamer to finish the surface. Then we're gonna use the tab to form the thread as we give rotation to this tab inside the workpiece. This is the tabbing operation. Counter pouring, it means that you already widening or increasing the diameter of the hole and the tip, and it is used for the counter bored pulse. Like one of the things, like the final product, basically, like assume that this is the work part. This is gonna be the work part. Initially we open a hole, but for some reason we would like to widen or increasing the diameter of this hole from the top. So if we're gonna use a bolt, this bolt is gonna be the head. Assume that this is a bolt. So the head of this bolt will be somehow, you know, like hidden inside this counter bore, and this is gonna be the bolt itself. So this is the bolt here that already inside the hole. So this is gonna be known as counter bored hole. To open counter bored hole, you have to use the counter borer. This is the tool. It is known as the counter borer. Okay, and you have to use the counter boring operation. The counter sinking operation, it is another, it do the same thing, but here we do have this hexagonal bolt. In case that we do have the bolt for this one, the final hole shape will be obtained in this form. So for this case, this is gonna be the work part, and this is gonna be the thing in the middle is gonna be the hole itself. So this one is known to do so to do this tapered head of the tapered head of the bolt itself, to allow for, you know, like putting this head or squeezing the head inside this tapered surface of the hole. We have to use this counter sinking operation. Center drilling is just to have a mark over the surface, just to do any other operation or something. So if you would like to have like a very quick mark, you won't gonna open the center drilling. It is basically not used for opening holes. We just using it for like pressing marks over the workpiece surface. Spot fishing, it is one of the operation like we just using it for finishing the top surface of a hole. Like if we do have this surface, and it would be rough surface, and definitely you're gonna use a bolt or something here. It should be super finished, so and super polished. It means that this surface should be very smooth surface. It shouldn't be any rough surface. So in this case, you're gonna use the spot facing operation. So all of these are different operations that can be done using the twisted drill or the drill press machine, or it can be classified as drilling operation. Make sense? The current fluid in the drilling operation is a big deal. What is the current fluid? This is what we are going to discuss. The current fluid, it is something that is used mainly it's used for two main purposes: to decrease the friction between the tool and the workpiece, and to get rid of the heat generated during the cutting operation. We said that all of this operation that we discussed for the drilling and even the turning operation, there should be a direct contact between the tool and the workpiece. This direct contact, you should have a tool that cuts into the workpiece. So there is a huge friction, right? Because there is a direct contact. There is a huge friction between the tool and the workpiece. And this friction, it will result into a very high force. As you know, friction produces heat. It will result into a very high heat that is gonna be generated. So as we do have a friction, the two surfaces, the tool and the workpiece, will be heated up. And this amount of heat is huge amount because of the high friction that already generated up on the direct contact of the tool with the workpiece. Another source of the heat, by the way, is cutting the chip. As we cut the chip itself, there will be some heat exposed because the material loses some of its part. So the material should overcome this thing through some generating more heat. So the heat resources are two things: the friction due to the direct contact between the tool and the workpiece, plus the breakage of the chip. this would reduce a very huge amount of heat. We have to get rid of it. If we just keep this heat as it is into the cutting zone, the tool will be heated up. Its temperature would increase more than 400 degrees Celsius, and this would break down the tool. Also, it would damage the workpiece that you already machining. So in so many operation, in most of the machining operation, we have to use a cutting fluid. The cutting fluid is a fluid. There is liquid thing that include water, in addition to some additive material, that the main purpose of this one is just to absorb the heat, is to take the heat away of the welding zone. I'm sorry, away from the machining zone, right? So this is the objective, and cools down. It is used mainly for cooling down the tool and the workpiece, but by removing the heat, by absorbing the heat, not so the thing that is going to absorb it is the fluid itself. In addition, it would include some lubricant material that would eliminate or decrease the friction between the tool and the workpiece. So in this case, we would reduce the amount of heat that shall be generated during the machining operation. So this is the objective of the cutting fluid, and we have to use it in many of the drilling operation. But how we can apply the drilling operation, during the drilling operation, how we can do the cutting fluid. So during drilling, heat is usually generated as due to different things. Friction between the twisted drill margin and the hole surface. What is the margin of the twisted drill? Which is the external surface. This is the margin of the twisted drill. This margin, it should be typically the same, which this one, this small thing, this is the margin of the twisted drill. This margin, it should be the same size, typically the same size as the hole, to give stability of the twisted drill inside the hole. But this margin will be in direct contact with the hole surface, so this will reduce some friction, and this friction, because of this friction, some heat will be generated. Another source of the heat is the friction of the sliding motion of the chip through the flutes. We said that we do have flutes here, and this chip shall be moving or sliding inside this flutes. So this sliding motion will result also into some heat due to the friction between the chip and the twisted drill. In addition, the cutting of the chip itself will generate heat. So we do have three sources of heat, or two main sources. Two is our friction. The second one is the chip cutting or chip formation, right? The friction between the twisted drill margin and the hole surface, in addition to the friction between the chip and the flutes. To reduce the temperature and remove the heat during the drilling operation, we have to use or apply a cutting fluid. How we can apply the cutting fluid? So there is difficulty in reaching the cutting edge, the cutting fluid, to the cutting point of the twisted drill. So we are applying, basically how we apply, like assume that this is the twisted drill that already cutting inside the hole. So we are applying the cutting fluid from outside, right? So, but it is difficult for the liquid to reach to the tip. This is the tip that we have to cool it down. We're gonna cool everything, right? Except this tip, the cutting edge itself. These two cutting edges won't gonna be cooled down as long as this twisted drill is inside the hole. Why? Because there is no room for the liquid to reach to the tip or to the cutting edge of the twisted drill. Why? Because simply the cutting point is surrounded by metal of the twisted drill and the chip filling the flute. There is chip was already inside the flute. And in addition, this tip is already inside the hole itself. So if you try to apply some liquid, there is no room for the liquid to move through the fluids to come into this two edges or the tip point of the twisted drill. Why? Because it is already inside. It is surrounded by metal from everywhere. It is surrounded by the metal due to the hole or the metal of the chip itself that already filling into the fluids. So that's why reaching or bathing the liquid to reach to the tip of the cutting point of the twisted drill, it is a difficulty that we're already facing during the drilling operation because of this reason. So therefore, to get rid of this or remedy this problem, what we are basically do, the twisted drill has to be removed out of the hole multiple times during one hole opening. While we open one hole, we have to open the hole for a while, then we have to remove the twisted drill to clean it and cool it down. Then we're gonna put it back again into the hole, open some part of the hole, then remove it back again and cool it down and so on. So we keep pushing or opening the hole or using the twisted drill and removing it from the hole for cooling down, then using the liquid to apply some liquid to the tip, then we're gonna use it again. So that's why we have to remove the twisted drill multiple times for that reason, right? So this is for the drilling operation and the turning operation. We still have two other operations, which are the milling operation and the shaping operations. So the next operation is the milling operation. It is one of the essential also machining processes that would be used. So the milling operation, forget about the name of the operation itself. You just focus on the operating principle as we did for the turning operation or the drilling operation. In the milling operation, it is mainly used for cutting straight surfaces. This is the main objective. But the turning operation, it is mainly used for making cylindrical surfaces. And the drilling is mainly used for opening holes, and the milling is used for making straight surfaces, like opening or finishing a straight surface, like these cases. So the tool, how about the cutting motion, the depth of cut and these things? The tool rotates in the cutting. This is the tool, it is commonly named as cutter in the milling operation. But the tool, it is named twisted drill in the drilling operation, and it is the single point cutting tool in the lathe machine that we didn't discuss so far, right? But the tool in the milling operation should rotate, and this what gives the cutting motion. But in the twisted drill, the rotation of the twisted drill, this is the cutting motion. The rotation of the workpiece in the lathe machine, this is the cutting motion. Here the workpiece is fixed in many of the cases, and the feed motion, it can be obtained by either the tool or the workpiece motion. It depends on the machine. There are some milling machines that we're gonna fix the tool over the table, and then the table is the one is going to move. There are some other machines that the workpiece is completely fixed, and even the bed and the table is not moving, and it is also stationary fixed, and the tool is the one that already rotating to achieve the cutting motion, and also like moving over the surface to achieve the feed motion, right? So the feed motion in the milling operation can be done through the tool or the workpiece, but the cutting motion definitely is going to be through the rotation of the tool itself. We do have two main configurations of the milling operation. The milling operation, it would be either plane milling or face milling operation. These are the two main types of milling operation. So that's why we do have two milling machines. We do have horizontal milling machine, we do have a vertical milling machine. The vertical one, it is used for making face milling. The horizontal milling machine, it is used for the plane milling. So what is the difference? In the plane milling, or also it is known as the peripheral or the slab milling. In the plane milling, the cutter axis of rotation is parallel. This is the key idea, is parallel to the workpiece surface during the operation. But in the face milling, the cutter axis, it is perpendicular to the workpiece surface during the milling operation. This is the big difference between the two methods. It means that in some cases, we may have the axis of rotation of the cutter. This is the tool. The tool, it is named cutter, commonly known as cutter in the milling operation. So the axis of rotation of the cutter, it is perpendicular to the workpiece surface. So that's why this is a face milling operation. This face milling operation. But in the plane milling operation like this one, the axis of rotation of the tool, it is parallel to the workpiece surface. This definitely is gonna be the plane milling operation or the slab milling operation. Make sense? Here the cutter for the slab milling, the cutting edge is outside the periphery of the cutter. Like what are the edges, or the cutting edge, it should be over the periphery of the cutter. It cuts with the periphery. So that's why it is named as peripheral milling operation. but here it cuts with the periphery and the face, with the end, with both the end and the periphery, with the face of the cutter plus the periphery. So we do have cutting edges over the face, which is the bottom surface which is not seen from this direction, in addition to the side. So for example, if I schematically represent it to you like the cutting tool of that would be used for face milling, like you're gonna find that this is the cutting edge that already located over the circumference, the periphery of the tool, plus it should have some tips here, like it should be also cutting from the face, from the end, in this way. So it has cutting edges over the face and over the periphery of the tool, over both of them. So this is the big difference between the face milling and the plane milling. The face milling, it is done over the horizontal, using the horizontal milling machine, horizontal milling machine. Because why? Because the tool, it should be horizontal, and it should be its axis of rotation, it should be parallel to the workpiece surface. But this one is done over the vertical milling machine. Make sense? So for the plane operation, it is not just one process. We would have a group of milling operations that can be classified as plane milling, or the common thing between like this operation. All of these are different examples, or different of the examples of the plane operation, and these are different examples of the face milling operations, right? So what is the common between this group and this group? The common between this group, that the axis of rotation, it is parallel of the tool, it is parallel to the workpiece surface. The axis of rotation of the tool is parallel to the workpiece surface on all of them. But in this one, the axis of rotation, it is perpendicular to the workpiece surface and should be done using vertical milling machine, but this group should be done using the horizontal milling machine. This is the common between them. So in the plane milling would have slab milling, and in slab milling the workpiece width, it should be lower than or smaller than the length of the tool. This is the tool length, and this is the workpiece length. It should be the tool length, it should be wider or the longer than the width of the workpiece. So for the slab milling, we're already machining the entire surface, all the surface, not part of it. Like all of this surface of the workpiece will be machined. This is the slab milling. But if we're gonna open a slot, like we're gonna open a slot like this case, we're gonna make this workpiece in this form. This is opening a slot in the workpiece or the work part in this way. Like you're just gonna open a way into the workpiece. So you're gonna use this cutter, sliding cutter in this way, and this operation is gonna be the sliding operation. Side milling, it means that we're gonna use the same cutter, but it's gonna, instead of machining the entire surface of the workpiece, it's just gonna machine part of the surface, and this part is gonna be on either side, the right side or the left side of the workpiece. So that's why it is commonly known as the side milling operation. Straddle milling, it is like this case, but instead of using just one tool to machine one side, you're gonna use two tools fixed over the same armor of the tool, and or the spindle of rotation of the machine, to give machining to both sides of the work part. Form milling, in this case, the tool will have a form, and this form will be imparted or copied to the workpiece surface. So that's why this would be grouped as forming operation or copying operation. But these ones would be considered as generating operation, because the shape of the final surface does not depend on the shape of the tool, but it depends on how you're moving the tool with respect to the workpiece. So all of these are generating operation, except this one is forming operation. So that's why we would have the name as form milling operation. Also, examples of the face milling, like the conventional face milling, and in this case the diameter. The thing that controls the operation here is the diameter of the tool. The diameter of the tool, it should be wider or bigger than the width of the workpiece itself. So for this case, we're gonna machine the entire face of the workpiece. For the partial face milling, and instead of having the tool to cut in the entire face of the workpiece, we're just gonna cut part of the workpiece surface. Like, so this is the partial face milling, the end milling, and this tool is known as the end mill. This is the end mill. This is very common tool that used in industry this way. The end miller is very similar to the conventional face milling operation, but the end miller is like, it looks like the twist drill, but the twist drill, it should have like 2 edges here, but the end miller have more than, it would have more than 2 edges, like 6 edges or 10 edges, or cutting edges, and it is used for sliding for lots of things. This is the end mill. But here we are using the end mill for just machining things or specific feature or shape over the workpiece surface, like opening slot, for example. We can use also the end mill for profile milling. In the profile milling, we are not for machining on the top surface of the workpiece, but we are already machining on the side surfaces of the work part. Like we are not interested in any machining to this surface during the profile milling operation, except that we would like to machine these surfaces, these side surfaces. These are the ones that shall be machined. So this is profile milling. You're just gonna ask the machine to move this end mill following the profile of the edges of the workpiece. So this is known as the profile milling. Pocket milling, we are using also end mill. This is the end mill. And this end mill is gonna be used for opening bucket, like you're gonna open some specific feature inside the workpiece, and this is known as the bucket milling. Also surface contouring, in this case we're gonna use the tool, but the tool should be go over a specific surface, and in many of the cases this surface, it should be like curved surface. So that's why we have to use something that related to the machine theory and the programming of the machine itself to achieve contour surfaces. And this basically is commonly done using the CNCs, which are the computer numerical control machines. But anyway, this is also one of the operations that can be done using the vertical milling machine and can be classified as an example of the face milling operation. Make sense? So again, we discussed the concept of the milling operation, and we said that we do have 2 different categories or 2 different methods of milling. We have the plane milling, that the axis of rotation should be parallel to the workpiece surface. We do have face milling, that the axis of rotation should be perpendicular to the workpiece surface. And these are examples of the plane milling. These are examples of the face milling, right? Now let us move to this very important comparison between the up milling and the down milling operation. You should understand that these 2 operations are belonging to the plane milling operation, to the slab milling operation. Both are plane milling operation. They are not face milling. So what does it mean? It means that for the up milling and down milling, these are not methods of or milling operation. These are 2 different approaches of doing the plane milling, or 2 different methods of doing the plane milling operation. Like in the plane milling operation, which is this one, the essential condition that the axis of rotation of the tool should be parallel to the workpiece surface, right? So for both cases, for the up milling or down milling, or the conventional milling or the climb milling, the axis of rotation of the workpiece of the tool is parallel to the workpiece surface. This is the cutting tool and this is the workpiece. So as we give rotation into the workpiece, there should be something that it shall be removed from the to the tool. As we give rotation to the tool, there should be something that shall be removed from the workpiece. The same thing here. But what is the difference between the 2 configurations or the 2 methods? In this method, in the up milling, the cutting motion, it is opposite to the feed motion. This is the direction of the feed motion, and this is the direction of the cutting motion. So the cutting motion and the feed motion, they are opposite to each other at the contact between the tool and the workpiece surface. But in the down motion, the direction of rotation of the workpiece, it is in the same direction of the feed motion at the contact between the tool and the workpiece. Like they gonna be in the same direction, but here they already having 2 opposite directions. So what is the difference? Both are plane milling, yes, because the axis of rotation is parallel to the workpiece surface. But in this up milling, we do have the 2 rotates opposite to the feed here in the same feed direction. So it is milling against the feed, but here we're already milling with the feed in the same direction of the feed. So what is the difference? The cutter rotates in a direction that is opposite to the feed direction, but the cutter rotates in the same direction of the feed. The chip starts out very thin and increases in thickness during the sweep of the cutter. For example, like it means that we already start the cutting from this point. The thickness of the chip, it is very small and it starts to increase as we go. So this is the part that shall be removed. So we start with very small thickness, then this thickness is going to increase as we give sweeping or rotation of the tool. But here we start from the high, we cut from the surface, but here we cut from inside. We start the cutting from here to there. But here we start from here, this is the start of the cut. So we start with a thick chip thickness, and with the thickness of the chip is going to decrease as we rotate. It is opposite. So we start from inside the tool, the workpiece, but here we start from the surface. We start the cutting from the surface of the workpiece. This is the difference between the two configurations. So that's why in this case, the chip starts very small, very thin, and increases the thickness as we sweep or we give rotation to the cutter. Here, each chip starts out thick and reduces in thickness throughout the cut operation. The chip is longer. The chip here we can form or we can obtain more chip, but here the chip is shorter. Here we can end up with a small amount. It means that the rate of removal here, it is kind of, we're removing more chip here than there. The cutter tends to lift the workpiece. As you can see, it moves against. So we have to fix, we have to use a method of fixing the workpiece over the table, right? This is one of the problems of this method, that we have to fix the workpiece against the table, because as you can see, this cutter, the cutting edges, it tends to lift up. So that's why it is known as up milling, lift up the workpiece. But this one, the tool edge or the cutting edge, it tends to push down to keep the workpiece in place. So it tends to hold the workpiece in place. So that's why this method is recommended in case that you have a small workpiece that it is difficult for us to fix it over the table. So the only option that we have to do it using down milling, because we are not planning to use a method of holding or fixing the workpiece to the table because the workpiece is too small. So in this case, the only option is just to use the down milling operation, because it tends to hold the workpiece in place, and the up milling is not recommended. But the up milling, it is preferred over the down milling in case that the surface of the workpiece is too tough. The surface usually for any material do have different properties than the bulk inside the material itself, the interior of the material. So if the surface, it is too hard surface to cut, because we start the cutting from the surface itself. So the down milling is not recommended, and the up milling is recommended over the down milling in this case, because we already, in case that the bulk of the material is soft than the hard surface of the material, so it is easy for us to cut from starting from the bulk of the material or the material interior, and in this case the up milling operation is preferred over the down milling operation. Make sense? So this is for the milling operation. Now let us move to the next operation, which is the shaping operation. Do the same. What is the operating principle of this operation? What is the different tools? And some things relating to this shaping operation. The shaping operation, it is mainly used also for cutting surfaces, very similar to the milling. You could say that the things that we can do using the milling operation, we can do using the shaping operation. So that's why this machine is not essential thing, or is not very common. The common machine, the essential machines are three things: drilling, milling, and lathe machines. Most of the operation that we can do by shaping, we can do them using milling operation and more. So that's why the milling operation is recommended over the shaping operation, and that's why this operation is not very common operation. It is one of the essential operation, yes, and it is very common, but it means that is fine that you can have a workshop with no machining or shaper. Okay, the shaper, this is the machine that you use for the shaping operation, but it is essentially to have a milling machine. It is essentially to have definitely this machine and twisted drill. Okay. The shaping operation, it is mainly used, as I said, for cutting surfaces. Like this case, you're gonna have, this is gonna be the tool, and this is gonna be the workpiece. And this operating principle, that the two reciprocating motion It's doing reciprocating motion, like it moves forward and backward, forward and backward. This is like repeating this cyclic motion all the time of the tool. This is gonna be the cutting motion. Like as the tool sweeps or like reciprocating over the surface, it removes chip and return with no cutting. Then it removes chip and return with no cutting, and so on. So it keeps moving forth and back, and so on. So this is the cutting motion. While in the meanwhile, the workpiece is likely to be fixed, and the feed motion in the shaper machine, it would come from the workpiece motion in the lateral direction. So how it works? Like for example, the tool cuts, remove the chip, then we're gonna push in this direction, this transverse direction. This is gonna be the feed motion to put more material in front of the tool. The tool is just moving forward and backward, right? Reciprocating motion. So while it moves forward, it's gonna remove chip, then it will return with no removing chip. Then we're gonna push. We're just gonna give like step pushing, like a little bit pushing of the tool into this direction in front of the tool to remove more chip, and repeat the process till we finish the surface. This is the operating principle of the shaping operation. In the shaping operation, we do have three different types of machines that would be used or can be considered as shaping operation. We do have the shaper machine, which is the main essential operation, which is the shaping. In the shaping, the tool is the one that moves reciprocating motion, and the workpiece is the one that achieves the transverse motion for the feed motion. Like the workpiece is held stationary, is fixed over the table, and the tool is on the ram. This is gonna be the ram of the machine. The tool over the ram of the machine is the one that moves back and forth across the workpiece to cut onto the workpiece surface. And it is mainly used for small workpieces, and it uses one cutting tool at a time. But in the planing, it is bigger. It is used with bigger workpieces, and it is more expensive tool for sure. That the tool is stationary, but there in the shaping, the tool is the one that is moving. But here the tool is stationary, and the workpiece on the table travels back and forth under the tool. So the reciprocating motion comes in the planing operation through the workpiece movement. But in the shaping operation, the tool is the one that moves while the workpiece is stationary. It is the opposite thing. It is used for large workpieces, but this one is used for small workpieces. It uses one tool at a time, but this one can use multiple cutter in the same time. Like we can fix one cutter on the top of the workpiece surface, we can fix another cutter on the side, another cutter on the other side, so we can cut with multiple cutters at once, because all of these cutters will be fixed, and the thing that is moving is just the workpiece is moving with respect to the cutter to cut chip. These are driven using the quick return mechanism, which is this mechanism that we are going to explain. It is mainly using the quick return mechanism, but this one, it is driven by the planer table, is either by gears or the hydraulic beams. By hydraulic system, it means that to achieve this reciprocating motion, we are likely using the hydraulic system or gear train system, which can support more forces. So that's why it can be used for large workpieces. But this one, it uses the quick return mechanism. This is one of the essential mechanisms that is already commonly used for the shapers or the shaping machines. It is less rigid and less robust. It means that it is not a strong method, and that's why it is used for small workpiece, and the rigidity and the fixation of the workpiece, it is not, or especially the tool, it is not that high like the planing operation. It is better rigidity that give more accuracy on machine surfaces, right? So this is the essential difference between shaping and planing operation. As you can see, I have compared between these two operations, but I didn't discuss this one, right? This machine, it is very similar to the shaping operation. It do the same thing in the shaping operation, but instead of moving the tool horizontal to cut over the workpiece surface, this one, you're gonna have the tool moving vertical, reciprocating vertical direction, the vertical direction, in order to open a slot in the workpiece. So the workpiece is held stationary, very similar to the shaping, and the tool is on the ram. This is the ram, but instead of having the ram horizontal, you just like this shaping operation is typically like sliding, but after you give rotation to the machine. Like you do have the ram is moving vertical, here the ram moving horizontal. So this is gonna be the ram of the machine, but here there is no ram. We do have the table. This is gonna be the table, and the table of the machine is the one that moves or achieving the reciprocating motion. Here the workpiece is stationary, fixed, and the tool on the ram moves up and down to achieve the carrying operation through sliding. It is mainly used for opening slots on small workpieces, uses one carrying at a time, very similar to the shaping operation. The rams are either crank driven or hydraulically driven. It is used the crank driven sliding mechanism, which the mechanism that used for this one, it is like this mechanism, very similar to this mechanism kind of. So you'd have a slider that moves up and down, and this is gonna be the crank. This is what we already studying in the kinematics class. It is less rigid and less robust, like very similar to the shaping operation. So this is what I want you to know about the shaping operation, is just to know what is the purpose, its operating principle, and the difference between these three different configurations of machines that would be used for doing shaping. And the common between them, that you should have carrying motion through the reciprocating motion of either the tool or the workpiece, and the feed motion is gonna be through the tool, also either the tool or the workpiece. Make sense? So that's it. This is the quick return mechanism that it is commonly used for the shaping operation. And this quick return mechanism, we already discussing this thing in the kinematics of machinery class, but it works in this way, that this is the ram of the machine, this is the ram of the machine, and this is the crank. This part is the crank. You're gonna have here a pin, and there is a slot in the middle. So as we give rotation, as already shown in the animation, as we give rotation to the crank, this pin is gonna start to just moving through freely through this slot to give rotation to this link. This link is just it is pivoted at this point, so it will rotate right and left to just move forward and backward the ram itself. So assume that this block is connected to the ram, which is this part. This block is the one that already shown in this, which is this one in the animation. Make sense? So that's it for these operations. So what we discussed so far, we just introduced what does it mean machining in general. Then we discussed the different operating principle of the turning operation, or the different common machining operation, like turning operation, milling operation, drilling, and the shaping operation. So that's it for this video, and see you in the next one.